also with ROM and RAM, their address size maxes out at 24.
Right, because 24 will give you 16 megabytes already.
Yes.
Which is a lot.
So what I had to do to get more than that was I had to use a series of multiplexers and then have multiple RAM.
Yep, that you have to do. Okay, so that's a good question. So the question is, given that if LogicSim has a limitation, like each register can only have up to 8 bits, how would you implement a 16-bit register?
Have them take turns.
Are we saying this is going to be a question on the final?
No, but this is a particular way to look at things. I mean, unless you guys have specific questions about the final exam, this is one of the things that that kind of tests whether you can problem solve, right? Because all the components that we need to make a 16-bit register is already here. We already know those components. So how do you make your own component, which is a 16-bit register, so that you can use it as if it is just an internal register or a register that is internal to LogicSim? That's the question.
Right.
Okay. So this is one way to do it. Okay. So you look at. I'm going to create a new circuit here. We'll call this register 16-bit wide. Okay. Register 16. So the way to do it is to utilize as many existing components as we possibly can. So we go to memory, and then we pull out 2 registers. So we have one register and another register here. Okay, and I'm going to stack it up like this. Okay, so now we can zoom in a little bit and look at these 2 registers. Now, when you look at these 2 registers, it really helps to kind of document these things. So we'll call this one the low byte. Okay, so we'll say low, and this one is the high byte. So we'll say this one is high. So now we have 2 individual registers. Every time you define a component, you need to have pins, right? The input pins, output pins, and so on and so forth. And we'll just say that with pins, we can have 16-bit pins because that's kind of what you need. So you go to wiring, and then you pull off the other pins. Okay, so here's my input pin, and here's my output pin. The input pin is going to be 16-bit wide. 16. And then the output pin is also going to be 16-bit wide. There we go. So that means we need a splitter to split the input pins into 8 bits in a chunk. The first chunk goes to low, the second chunk goes to high. And then the output is going to be reversed. So now we need a splitter. And the way we do splitting is very specific in this case because we need to have a fan-out ratio of only 2. But the bit width of the entire thing is going to be 16-bit wide. So when you look very closely, it is already, it's doing the right thing. It is evenly distributing the bits so that the upper split is bit 0 to 7. The lower split is from bit 8 to bit 15. So this is the right split already. So this means I can now take this splitter and then hook up the lowest 8 bits to the low register, the input of low register, and then the upper bits to the high register. And then the pin itself is just connected like this, and we are done with the input. With the output, it is exactly the opposite, which means I'm going to duplicate this one, just flip the direction, make it face west, like so. Okay. Take Q of the first one, put it into the lower bits, take Q of the high bit, high byte, and now we have these 2 done. So now what we are left are the other pins, the control pins, right? Enable, clock, and reset. They can be shared. So the 0 pin or the reset pin is really just kind of shared between the 2 registers, and we'll make one single input pin corresponding to that. Okay, make it face west, like so. The clock pin, same way, okay, they can share. So we'll hook up these 2. And define a input pin for just that. That becomes our shared clock pin. Enable is the same way. So now we have these two. I'm trying to preserve the same locations, so this way the shape of this register will be the same as the shape of the 8-bit register or the internal register. Okay, so here's your 16-bit register made out of two 8-bit registers. But from the external perspective, it is acting as if it is a single 16-bit register. Yep.
So what I'd have to do essentially, since I was trying to go over 32 bits, and you can't bundle wires in Logicep more than 32 bits.
Okay.
So what I would probably have to do is I'd probably have to have 2 output pins for the high and for the low.
Oh, that would be
And
troublesome. Yep.
Yeah. The trick is, how do I get it to interface with the RAM and the ROM? You know?
Okay,
And
so
getting the
that's a
output
good
there.
question. Okay, so the question is, when you, okay, do you guys remember from our previous discussion? With a modern processor, every time you go to memory, you're not getting back a byte.
Yeah.
Okay, depending on the width of your data bus on your motherboard, every single time you get something, you may be getting back 128 bits. You may be getting even more. It's actually wider than the width of your processor itself. If you have a 64-bit processor, each memory access can be getting back 128 bits instead of 64 bits.
Right.
That's why you have 4 memory banks, and that's also why, you know, if you only populate 2 of the 4 memory banks, you only get, you know, some performance. But to maximize performance, you want to populate all banks, you know, of your motherboard. So it's the same thing with Logisim. In other words, you know, what you can do is you can split it up so that one RAM chip supplies, you know, the lower 8 bits or the lower 32 bits or the lower 16 bit, and then the other RAM chip supplies the upper, you know, 16 or, you know, 8 or 32 bit. Which is exactly how it really is done using, you know, DIMMs, dual inline memory modules. They use the same mechanism.
Right, I was going over that portion of the lecture over and over again as I was trying to model it. I'll show you it in the lab I have.
Okay, that's basically what that part is.
Yeah.
All right, so regarding the final exam, okay, first question is, what can I bring to the test from the perspective of a student? What do you guys think?
Everything we brought from the last 2 exams.
It's open book, open notes, okay?
Yeah.
The only thing I really have a problem with, you know, which is, you know, outside, which is an exception to what is printed or handwritten prior to the test, would be exam from the other class of the same semester. So that would be a no-no, okay? Which also means that, you know, the exam questions of the 2 classes would not be the same. Yep.
But exams from previous semesters are okay.
Yes, exams from previous semesters are okay, but just not from the same semester.
And the exam is on Wednesday.
For this class, let me look it up. I'm going to look up, you know, the ARC website.
Wednesday at 10:15.
Oh, that's the wrong place. Well, it is the right place for some of my classes, but the wrong place for this class. So we go to.
You can go to A to Z site index and just Control F for
final.
schedule. Yeah.
Okay, because I want to double check and make sure, because sometimes I may not look it up correctly. So I'm going to go for the source. And this is a Monday, Wednesday class. Start time is 10:30. So it'll be this one. It's going to be
So classes from then are going to be on Wednesday, December 13th.
Wednesday, December 13th.
Get the scroll right. Where's this one?
Yeah.
10:15 and 12:15.
Yep. So next Wednesday is the final exam date of this class, and the time is 10:15 to 12:15, which is great because people who are also in my 440 class, now you don't have 2 back-to-back exams. In the spring semester, for some reason, they're always back-to-back, even though, you know, but in the fall semester, somehow they're not. They're spaced out.
And this is the last class day.
But that's mean you have to come back here on campus one more day.
I have another exam that day, so.
Oh,
I'll be
okay.
here late.
Yeah.
I can use the, maybe use the morning to study.
Or maybe we
Okay.
can go to the other one.
Okay, so is that clear? Does everybody understand when or on which day the final exam is and at what time? So remember, it's not 10:30; it is 10:15. So arrive a little bit earlier than usual, so that you have time to settle down, lay out all your stuff. I will probably let people in by maybe 10:05 or so, so that you have some time to kind of just sit down, calm down, lay out all your stuff, and get ready.
Try softly yourself.
Mm-hmm. Yep.
Meditate.
Some people may pray. Some people may self-medicate.
I'll pray afterwards.
What if I asked her?
Okay, so how are you going to prepare for this test?
Wing it.
The exact same.
Sorry?
Wait, is it open book?
It's open book, open notes. So you can bring anything that is printed or handwritten prior to the test. So that means all the examples that I go through in class, you can bring those. My solution to the homework assignments, you can bring those. Your own solution to the homework assignment, you can bring those. All the previous exams, except for the Tuesday, Thursday, final exam, you can bring those.
Which will be after anyways. Which will be on Thursday anyway, so we can't.
They're on Thursday? Oh, okay.
Couldn't even.
So you have to worry about them taking our exam.
Unless you're a Time Lord, then you can travel in time.
Well, I think there are bigger problems with Time Lords.
I don't think Time Lords will need to take this class.
Yeah.
So if I was a Time Lord, I wouldn't take their exam. I would just wait for you to grade ours, steal the exam from you, and then go back in time.
Yep. So, how do you study for this class? It's the same way that you study for exam 2, okay? Or the same way that I would suggest people to study for exam 2. So everything starts from this picture, okay? So you gotta make sure that you understand everything in this schematic, okay? Which starts with a few things, okay? So it starts with you understanding what a multiplexer is, what a demultiplexer is, what are these tunnels, right? What is a register? Okay, so we got plenty of registers in this case. So you got to understand all the pinouts of a register, what they actually do. You have to look into the register bank itself. So I will bring a schematic printout of the register bank itself and understand how the register bank itself operates as a whole. You have to go back and look at the ALU, which is a little bit more complex, but nonetheless, it does not have any real additional components. So the ALU is different in the sense that it has got an adder, a subtractor, a right shift operation, a bitwise NOT, a bitwise AND, and a bitwise OR. Okay? Everything else, are basically basic logic gates. Like the way we compute the Z flag is a NOR gate. Okay? It is a negated OR gate. The way we do the computation for overflow depends on whether it is an addition. So this part of the circuitry is for overflow for addition. This part of the circuitry is for overflow for subtraction. They are different. Okay. You have to know how this multiplexer and this multiplexer is integrating the results of the operation, so that we have one single overflow output and one single carry output. Now the carry output and the overflow output, you can see that it is kind of strange because I'm just copying whatever is coming in to become the output for all of the other operations. The only two operations where overflow and carry can be different from what is coming in are addition and subtraction. Because when you're doing bit shifting, it makes no sense to ask the question, is it overflowing or does it have a carry? Same thing applies to bitwise NOT, okay? Or bitwise AND, bitwise OR. For those operations, there's no such thing as overflow nor carry. So are we doing okay so far with this discussion? So I would definitely understand the schematic and bring a copy of the schematic with you for the exam. Is that okay?
Yeah.
All right. So this is important. Okay, getting back to main here. So this entire diagram is important. And then what is also important are the instructions, or what is in the ROM microcode slices over here. But this table, okay, if you print out this and bring it with you, it's not going to be very helpful because you're just looking at a whole bunch of hexadecimal digits, right? So the best way to look at this is to look at the whole thing, but decode it. And the way to decode it, there are several ways to do it. Let me one. Okay, this is good. Big enough. Okay, so the way to do it is you go to the opcodes folder, and then you look at each instruction. So let's say we just look at the JC instruction here. So you look up jc.c, and then ucode.c is also the file that you want to look at the same time. So once again, the table or these slices are defined so that this entry, the first entry, corresponds to the first entry here. So when you look at the ucode definition, the first number corresponds to the width of that particular bit field. The second number corresponds to the bit position. So bit 25 by itself is microcode pointer reset. Okay, when that pin or when that bit is a 1, the microcode pointer, which is a register, is going to be cleared or reset. Some of these have multiple bits, like PC MuxMux is at bit 20, but it's a 3-bit field, which means it takes up 3 individual bits, so they can specify a binary 0, 0, 0 all the way up to 1, 1, 1, because that particular multiplexer has 8 inputs. So in order to select one of 8 inputs, you need to specify 3 bits, and that's why PC MuxMux has 3 bits, or it's 3 per byte. So that's this is also something that is important, and if you do not have a table already that shows you the microcode slices of all the current instructions, you might want to make one and bring that with you in the exam. Because whenever we have a question that requires the implementation of a new instruction or the modification of existing opcodes, you need to know how current instructions are making use of those individual bits, so that your modification of the processor is not going to have backward compatibility issues. So your current homework assignment, which is due next Tuesday, is going to be a help because it forces you to look at all of these things and consider all of these factors.
Oh, yeah.
Okay. Yep.
Let's do Tuesday, not Monday.
Oh, on Monday. Okay, I got confused.
I'll
Yep.
make the extra day.
No.
Don't think I'm complaining.
It is Monday. Okay.
Dang it.
I cannot track my day of week. And I cannot use students either because I see certain students on Tuesdays and Thursdays because they are in another class. Not mine, but when I walk out of the classroom, it's like, is today Wednesday or Tuesday?
Or someone decide to show up in a different class. If it's the same class, if someone decide to show up in the Tuesday, Thursday class, this one can be new.
For lectures, yes, they can show up, on either one. But for exams, they have to show up in the
They
correct
shouldn't
one.
have any conflicting with it. The final schedule is made in such a way they should.
Oh, I know. For fun, I was just saying.
Yeah.
Throughout the semester.
Yeah.
Okay, so this is the second piece, that you kind of really need to read. There's no need to understand exactly how these particular functions work because they're kind of internal. Read ROM, write slides, those are not as important. Okay, so this is the second part that is kind of important, and I would make a table out of this so it's easy to look up, either by instruction or by a particular bit field. So you can say, okay, this new instruction is gonna do something with this data bus. What can potentially be interfering with this new modification? You just look up, the control lines across all the instructions and can go like, okay, this instruction potentially can drive the data bus. This one can drive the data bus, and so on. Is that okay? So then we also look into, okay, this time I have to go back to the website itself. So we also look into all of these things in assembly programming. I'll do you guys a favor. We are not going to go back to floating point representation in the final exam. Would that help?
Yes.
Floating point representation. Double.
There's 2 ways of doing it. Okay.
There's
Yeah,
the
ways
fast
of
way and the
Yeah.
way is we know.
To do what?
To the floating point.
You can shift it and compare.
I'm meeting with it.
Well, because like I have the idea of like how the computer does it, like how it shifts the 10-bit or the base 10 number, and then there's a way where you subtract like 0.5, 0.25, stuff like
Compare and
fractions.
subtract.
Yeah. So I find that way of subtracting fractions is easier, but then I mix the two up.
Well, but that way is only usable when you're manually doing it, because it's difficult to program that into an algorithm. So floating point is not going to be in the final exam unless somebody contests and go like, no, I insist that we need to have a question on double.
Can we do binary addition?
We'll have to write.
I like what he's saying over here.
What? What did he say?
I asked for binary addition.
Or subtraction.
Yeah.
Never plugs those two.
Either one of those is good.
How about, to make it fair, how about multiple cases? Okay, subtract here and now subtract here. Or add here and subtract here.
How about double subtraction?
No.
Better than nothing.
I'm not complaining about that.
Double subtraction is nasty because the first thing you have to do with double is you have to align the binary point before the subtraction.
No, thank you.
So you have to look at the
How about
exponents.
double addition?
Same thing. Double addition, you have the same deal.
How about with decimal numbers?
Oh, you mean?
I mean real decimal numbers.
How about we have to take two separate things, two different binary codes, add them together, and then figure out what they would do if we fed them in.
I am not on board any longer.
Okay, so the bottom line is, that stuff is out. The carry look ahead and borrow look ahead is also out of the final exam. So no need to focus on those things when you're studying. Okay. So the final exam is really going to be focusing on this part of the class, assembly language programming. Okay, which to some people is good, to some other people is not so good. It all depends on which part is kind of your thing. Calling and returning from subroutines is important. Yep.
So I just wanted to clarify, there's only going to be questions from the assembly language programming on.
Unless it has dependency to earlier concepts.
Okay, but
Could you give us an example, just so we have an idea of how it would be dependent on early concepts that you would?
Like when,
Would you have to use logic?
like when you compare. Okay, if I give you code to translate into assembly, and I give you a comparison, and inside the code there's a comparison. Okay, if x is less than y, then blah blah blah. Okay, so which instruction you use for branching now depends on whether they are signed or not. If they are signed, okay, which flag do you use for branching? Well, that goes back to the earlier concepts, right? When we talked about binary subtraction, we talked about the carry flag, the overflow flag, the sign flag, and then eventually the L flag. So there's dependency on those concepts. But I'm not going to ask you about, okay, how many clock cycles do we need to go through with a 8-bit adder that has carry look ahead, and the fan-in ratio is only 2 to 1. Okay, so that is not going to be in the test.
Makes sense.
Okay. All right. So getting back to here, calling and returning from subroutines is going to be very important. Returning a scalar value is really simple because it is just through register A in the case of the toy processor. Passing parameters is important. And then it's from here on, it really is just a matter of looking at C code, translate into assembly code, or vice versa. Or I can give you both versions. I can give you the C code, I can give you the incorrect assembly code, and then you guys have to fix the error. It's like, okay, what is wrong with this code? Yep.
So is it pretty much just like the same as test 2?
It'd be very similar to test 2 because we have introduced very little content, after exam 2, which is kind of nice in a way because it means I really have talked about everything that I needed to talk about in a semester.
Okay.
Yep.
How many questions are we expecting on the
About 5, 6, depending on the complexity of the questions. I will also make all the questions, carry the same weight, which will make it easier for you guys to decide, which one to deal with first. because the general strategy is you find the easiest question to begin with. But if the questions carry different weight, then you also have to factor that in and go like, oh, this is a really easy one, but it only has like a tiny fraction of the entire test in terms of weight. Should I waste time to work on this one, or should I work on something that has more points? But if they all have the same point values, then it really is just looking for the easiest one to start with.
What do you know?
Huh?
What do you know rather than
Well,
what can you figure out?
exactly, the one that you can start working on right away, you feel the most comfortable with. So as usual, you have to time yourself. Just make sure that you don't spend too much time on a single question. Yep.
Can you remind us how much the final exam is worth? How much? 30%?
40.
Okay.
Yeah. So it's worth 2 exams. The 2 of the midterms. So it's kind of heavy duty in that sense.
Do you drop a question?
Yeah, I dropped. I dropped the question in the first exam. I have not finished grading the second exam yet, so I'm not going to. I cannot be sure whether I will be dropping the lowest score in the second exam.
Do you drop a question depending on the class, how the class did on that question, or depending on how
it depends on how the class is doing as a whole.
So do you drop a question per, like a different question per person, or is it a general question per?
I dropped the lowest scoring question, so each person. So there are 5 questions, right? So each question, so it depends on the person. For someone who did not answer any one of the 5 questions, it doesn't matter, right?
Yeah.
For someone who answered all questions and they all received full score, it doesn't matter either. So it will only matter to people where they have questions that have different points. So the lowest one is going to be dropped. So people who score perfectly before the adjustment won't benefit from it because they're 100%.
I'm happy that I studied so hard and now I don't get the full reward of my study. I could just skip the question.
I think some confidence.
You could just skip a question. You felt that confident.
But don't skip questions because that's based on the assumption that I'm going to drop one. Okay,
That's
so
true.
which may or may not actually happen. So don't count on it.
So I'm saying that takes some confidence right there just to skip the last question.
Exactly.
But you still want to prioritize, okay? And just go with the easiest one first. Whatever looks the most difficult, leave it at the end, okay? So that you, in case you run out of time, you will still score as many points as possible with all of the other questions.
Did you give us a practice exam, quote unquote?
It's in the share folder. It is.
Yeah, because it's going to be very close to exam 2.
Yeah.
So we did go over many of the final exams when we went over exam 2 already. So it's going to be about the same. Yep.
Is it possible if we can get like the second exam? Is that possible online? The one that we just took. I was want to get that.
Oh, I can put it there.
Is that possible?
Yeah.
So it's kind of.
You went over it in lab and you reported it right, the answers.
Yeah, we went over all the questions, but I think he wants to have the actual
I do too,
text
yeah. Yes.
of the question.
Yeah, that'd be good, just to run.
I also have those in my office too, so if you want to get your own copy, that's fine too. Yep. So let me share. Exam 2. And this class is going to be, I cannot remember, is it A or B? You guys will not know, only I will know.
Did you give us both?
Oh yeah, we can do both.
Don't say why not.
Okay, so we'll copy to.
Big copy.
Make a copy. There we go.
Are you mostly doing programs or frames?
Most ASP have that. Most of ASP have that.
And then we'll move this to shared. And this is exam 2. I'm gonna make a new folder for old exam 2.
I don't know about much.
Okay, so that one is now shared, and I'm gonna do the same thing with this one.
That's fine. I would rather.
It's all soft.
Do you have the average of the score of the first exam of the class?
Hmm?
Do you know the average of the score of the first exam of this class?
I do not know offhand,
Okay.
but I can find that. If you send an email to me, I'll find it and make an announcement so that the whole class can know about it.
Would you have exam 2 graded by then?
Huh?
Would you have exam 2 graded by next week?
It'll be soon. You know, I was planning to get it all graded last night, and then something happened. Something happened. I was just saying that something happened.
So, and you
I'm
probably
guessing something to do with the cat.
No, not the cat.
Summer after graduation.
Yep.
You probably already answered this, but is my final going to be curved?
I'm not curving unless I have to. So it'll just be a straight score, you know, for the most part. Okay, so the exam 2 are now shared, you know, through the folder, so you guys can actually look at your own exam and also the exam of the other class. You can kind of do the comparison and find out what I tweaked, you know, between the two exams. Okay. So getting back to, you know, how to prepare for the exam, there are a few mechanisms that we talked about in this class. Translating from C to assembly code is never about C++. So you don't have to worry about inheritance or, you know, classes, virtual functions and stuff like that. You know, I used to teach cisp310, and guess how I taught that class? I translated, you know, C++ code into regular C code and showed the implementation of all of those, you know, concepts, but in C.
Why?
Why
though?
Because that will show you, you know, how a particular mechanism is actually implemented, like a regular member method as opposed to a virtual method.
How do you
So you're getting
represent
closer
a
to
class
the-
in C?
Huh?
How do you represent a class in C?
You cannot represent a true class in C because the syntax does not allow that.
Yeah.
But I can show the mechanism of how a particular object can get to a particular member method by looking up a table. But the mechanism of a virtual function versus a non-virtual function is entirely different, because one is attached to the static type itself, the other one is attached to the object itself. And also casting, you know, those are all kind of interesting mechanisms. Okay, what I'm going to do is to turn on my tablet, just so that we can, I guess, you know, it's mostly text anyway, so I would use the tablet only when I need to.
Another question, you probably don't know this on top of your head, but do you think you can also find like the question that the class did the worst on, and you probably post that question so that we can kind of like focus on it? Because I feel like there's a question out there that a lot of people probably just didn't do well on.
I do not know offhand, but I can
I
can find out.
Yeah, I'll send you an email. I'm curious too.
Yep. Okay.
Sure.
That works. Okay, so C to assembly translation. Assembly. Okay, so there are many things that we have talked about already here. The first one would be control structure. So when we talk about control structure, we're talking about the conditional statement, the pre-checking loop, the post-checking loop. Okay, these are the only three that I really, you know, use in this class. So there are no switch statements. There are no for statements. You know, just these usual, you know, three statements.
You can write a forward loop as a while loop anyway, so it doesn't really matter.
Exactly. A switch statement, the implementation of a switch statement depends on the constants for the switching. Sometimes it's done by conditional statements. Sometimes it's done by table load.
Just do go-tos for switch statements. The switch statement could just be done with go-tos.
Yeah, it's really messy because, you know, a switch statement inherently would fall through the cases, but a conditional statement does not.
Yeah.
Okay, then we talk about subroutines. So when we talk about subroutines, there are a few subtopics. One is how do we call a subroutine, and when you are in a subroutine at the end, how do you return from a subroutine? So these two concepts were introduced first, and before that we talked about the stack concept, right? You know, what is last in, first out, you know, which is the concept of a stack. And then we talked about parameters, local variables. And parameters is kind of interesting because you have to remember that the last parameter has the highest address, and first parameter has the lowest address, and it's always right next to the return address.
By highest, we mean 252 would be higher than 253.
250,
So the stack starts at 255.
right.
So the highest is 255, or is the lowest?
The highest is 255.
So the return address would be at 255. Oh,
No, the return address is the
Put on
lowest.
last. Yeah,
The
right.
return address is below the first parameter
Right. That's
in the
what-
subroutine call.
that's what-
Yep. So we talked about local variables, and local variables, for the most part, are kind of like parameters, except for two things. One, local variables are allocated by the callee and not by the caller. And two, local variables cannot be initialized by the caller because the caller doesn't even know what kind of local variables are in the subroutine that it is calling. Now, with parameters, there are several things that we also have to kind of pay attention to. The caller cleans up parameters. The callee just makes use of the parameters, but does not do any cleanup. The caller is the one responsible to clean up the parameters. So after a function call, when the callee returns to the caller has to deallocate those parameters out of the stack. Okay. Local variables are deallocated by the callee. Because the caller has no idea, how many local variables are used, and those are all below the return address. So that's why it has to be the responsibility of the callee. When we talk about calling and returning, this is the interesting part. Caller is the one that pushes the return address, but it is the callee that's going to be popping it or removing from the stack. So you have to remember that this is the only exception to the rule where the caller is the one that's pushing, but the subroutine is the one that is popping. For everything else, if the caller pushes on the stack, the caller cleans it up.
Should, for what's the consistency, should the parameters and local bars notes say pops? Parameters, pops, local bars?
Not exactly. The word pops means, not only are you cleaning up, but you're utilizing those values that you have put on the stack.
Oh, okay.
When we use the word clean up, it means that you're just deallocating it, but you're not putting it into some place that is useful. Okay. Okay. So when we talk about the stack, subpoints here is kind of the register D is the I was about to say de facto standard, so we'll just say that is the. We will just say that it is the stack pointer for the toy processor.
A is the return.
Okay, callee can use register A, B, or C, which also means whenever you perform a function call, everything that is in register A, B, or C may not be preserved. So if the caller says, oh, register B has something that is really important to me, and I want that value to be retained in register B, the caller will have to push it on the stack before making the subroutine call, and then when the subroutine returns, the caller can pop it from the stack to resume that particular value. Okay. We also talk about return values. Okay, so we'll put it here. Return value is through register A, but only for scalar values. Okay, in this class we never talked about returning a structure because the toy architecture is a little bit too small to really talk about structures. But that's why we don't worry about how to return a structure in C. But the features is in the C programming language itself. It's just that we never talked about the mechanism of how it is done. Okay. All right. So then we also have other general topics in C, programming. So when we talk about C programming, we already talked about the control structure here, but we also have talked about pointers. Okay, how do you dereference a pointer? When you have a parameter that is a pointer that is stored on the stack, the first thing you need to do is to find the address of the parameter. Then you can get the value of the parameter. But if the parameter itself is a pointer, you can potentially dereference that pointer one more time to find out what the pointer is pointing to. I think in the second exam, a lot of people forgot about the second dereference. because one of the questions, has a dereferencing of a pointer that is a parameter. Many people find the parameter itself, but then forgot that there's one more dereference to go to where the parameter itself is pointing to.
The content.
Yeah, but I didn't deduct a lot of points. If you look at the grading or the rubric, I broke things down into like tiny little components. So if that component is missing, you're just missing that one point out of many, many other points. Okay, so we talked about pointers. We talked about pointer arithmetics. You can add or subtract from pointers. You can even subtract two pointers in C and C++. Yes. So, okay, so maybe it's.
Content of the pointers or
No, it
just
sounds.
Yeah,
No,
the
the address.
Well, pointer arithmetic
It's
sucks.
the distance between.
Oh, you're talking?
Yeah.
Okay, just show me.
No, but I just don't know what you would use it for.
Okay, so you can have
Right.
P2 minus P1, which is a pointer subtraction. Now the question is, when you subtract P1 from P2,
Something.
what is the type of the result, and also what is the value of the result? Okay, what do you think? First of all, what is the type?
Of the result.
The type is an integer. Okay, so the type is an integer, but what is the value? It is the number of t's between where P1 points to and where P2 points to.
So it's the
Is that for like?
it's the jumps of memory.
Yes.
Yeah.
It is the number of things, the number of objects of type T that you can fit between where P1 points to and where P2 points to. But this can be positive, it can also be negative. It can go in either direction.
Are you referring to T
So
as
one is further
class
down the
template?
list. Well, which one, other than like, I assume for cache or calculus or whatever things like that, the only reason we want to use that is to see how efficient memory is used, or is there an actual application to where you would want to use to know the distance between 2 points?
Okay, so let's say you're going through an array,
Yeah.
okay? You're looking for something.
Oh, right.
You're looking for something else,
Yeah,
and you
okay.
want, occasionally you want to know how many things are between these two.
Yeah.
Then a pointer subtraction.
I
can give
remember
you
now,
that.
yeah, that was what it was used for.
Yep. So just remember, we are not counting bytes in the subtracting the difference. We're counting the number of whatever t is, between those two locations.
Integers, doubles, so on.
Yeah, it can be structures. Okay, we don't use structures in our class, but in general C, it can be structures. T can be a struct, blah blah blah, can be a class, blah blah blah. But you're basically looking at the number of items between the two pointers. And it can be positive, can also be negative, depending on which one is less. Okay?
This is semantics, but type space asterisk variable name or type asterisk space variable name.
That is semantic.
For declaring a pointer, why do people prefer? I see that all the time. It's type space asterisk and the name, but it confuses me because you think it'd be type asterisk would be.
I remember somebody.
but
You can do that too. That's legal.
Yeah, that's really
that's just disgusting.
But like it would make sense to me. You'd say it would make sense to me. You say it's a pointer of type T, and I'm calling it P1. It just looks weird. I don't know.
I guess it depends on whether you are type-centric or whether you are variable-centric. Where you say, okay, what is P1? P1 is a pointer to a type T, as opposed to type-centric, where you say, okay, I know what a type T is. How does P1 relate to it? Whatever P1 points to is a type T. So it means exactly the same thing. As you said, it's all semantics.
Yeah.
But it depends on the person. Some
Right.
people are more type-centric and other people are more variable-centric.
And then there's
Yep.
also.
Could you technically also just put another space between T and asterisk?
Yeah.
Yes, you
that's
can.
That's just weird.
I don't like you.
Space
Wait, people like me?
It's undecisive. It's just you couldn't choose. You just put it in the middle.
Yep. So we also talked about recursion.
Oh, I
and-
know why people do that. So,
Yep.
so usually you want to put it between for the pointers because if you just put the asterisk up right in front of int, then if you do like a comma in the next one, you're not implying that The next one is not a pointer, it's an int, right?
Oh yeah, you can
so
do that.
You want to
Yep.
do it in front of a variable name so that you
Oh,
know.
so it's.
Yeah, because when you say int, the asterisk is only going for the next variable.
It gets messy though. That's true. That makes sense.
Exactly. That's different.
Yeah, but you shouldn't do that.
It's really messy because then you can't talk about, okay, what is this used for? You're just declaring.
Can you do
function.
this in C?
You can't. It makes it terrible.
You can't
to read.
declare. I don't think you can declare C with an empty array unless you.
Yeah, you can.
Unless you
C style,
define
yeah.
its contents. I thought you have to define its contents.
There's a C style way that you can.
I think this is the same thing as star C. It's equivalent.
No, that would make sense.
Yeah. Oh yeah.
Yeah. Okay,
Point
so
zero one.
we also talked about recursion, and from our perspective, if I give you, okay, this class is never about creating an algorithm that is recursive. It is only about implementing a given algorithm that is recursive.
Which,
So from that perspective, whether it's recursive or not, really should not matter.
as long as it's tail recursive, it's easy to turn into a loop, which is then easy to turn into a.
Yeah, but in your implementation, I'm looking for a literal translation from the C code into assembly code.
It's easy.
So it doesn't make any difference.
Yeah.
So in other words, I really think that no one should be bothered by recursive subroutines in this class because it is not about you creating a recursive algorithm. It is about you implementing a recursive algorithm. But whether the function is calling itself or calling somebody else should make no difference. The mechanism of passing parameters is the same. The mechanism of calling and returning is the same. The convention of registers A, B, and C can be modified. It's the same. The concept of returning a value through register A is the same. So it makes no difference whatsoever whether you're calling the function that you're already in versus calling some other function. It really should make no difference. Does that make any sense? Okay. And I'm also kind of really hoping that because the way we look at how the stack is used, how we pass parameters, how we allocate space for local variables, that any mystery that we had about recursion from previous classes is now cleared up. It's like, oh, okay, we understand exactly how recursive algorithms work. Is that kind of the case or not? Okay, very good. Yeah, so the only other thing that we kind of talked about also is decompiling. Okay, so when we decompile, which means we're given the assembly code and you're reversing it back to C code, that process is kind of the reverse of translating from C into assembly code, but there are some additional things that you have to kind of infer, right? Okay, so signedness can only be inferred by conditional branches. JCI doesn't give you a single clue because JCI is the same whether it is signed or not, because you're just looking for you're looking for equality in this case, or whether something is zero. Whether it's signed or not doesn't tell you anything. Okay, does not differentiate.
I would have did that as JCI equals question mark.
Mm-hmm.
Well, usually with a JL.
So JCI versus JLI does make a difference. Okay? Differentiate between signed versus signed. Okay?
So JCI will be, those are,
Okay, maybe I'll make this even more clear.
yeah. Respectively, yeah.
There we go.
Okay.
Okay.
I know that word, has some use in some situations. Respectively, yes.
It's used for that.
Exactly.
It can be respectable to use.
Hmm?
You can say the former or the latter.
I think it's only respectively. Respectful has to do with communication between people.
Can you talk respectfully to a machine?
Now you can.
Good job.
What's the rubber ducky method? Like you have a rubber ducky and you explain your code to the rubber ducky to help you debug.
You can now explain it to Sophia.
Oh,
Sophia becomes your new rubber ducky.
but I don't want to respond. I just want to listen.
I've read about the rubber ducky thing.
That's because when you verbalize, you are using a different part of your brain. and as a result, your thinking pattern is different, and certain things that was not clear when you're just thinking is now becoming more clear because it involves the part of your brain that is more symbolic.
I'm sure you've done the thing where you're thinking about something and you ask somebody, and then while you're asking that person that question, like you figure it out mid-sentence.
Yeah.
Like, oh, never mind.
Yep, exactly. Yep, it's interesting how the way we think, the way we come up with words, links to the way that we think. That would be the best way to describe it. Okay, so when you're decompiling, this is important. Order of parameters. Okay, so how do you know which ones are parameters? Okay, parameters have addresses higher than the return address. Okay, cool. But where's the return address? The return address is always pointed to by the stack pointer at the entry point of a subroutine. In other words, register D always points to the return address when you're at the entry point label of a subroutine.
So that's why we assign D to like register C, and then we decrement.
Exactly. So that when we modify C, it doesn't really modify D itself, but it gives us a reference point and go like, okay, which part of the stack are we referring to?
Are we allowed to use D and just remember where it is?
How do you remember where D is?
Type here. Okay, I decremented one, decremented twice.
Store the stack pointer in a...
Yeah, you can. That's the only way to change D and restore it is to decrement and then increment it back.
Right.
Yeah, but you don't want to increment and then decrement it back because the moment you increment, whatever is below the stack pointer points to is subject to be changed. When you have interrupts. So even though the toy processor does not have the mechanism of interrupting, we still want to follow those rules because because I want to teach what is going to still be useful when you guys have to deal with processor architectures in general that have interrupts.
But if we're in main, we can decrement or increment D to allocate by its own stuff.
That's correct, because that basically is corresponding to the initialization of the entire processor.
Okay.
So that part is okay.
But if you explicitly state we're in a subroutine and we're recursively calling to a different subroutine, then that's a case where we're not in main, we're already in the subroutine, and we shouldn't be using increment D to allocate by its own. But yeah, my point is like we shouldn't be using this stack pointer.
Right. So with the stack pointer, you should, when you're allocating, you decrement.
Yeah.
When you're deallocating, you increment. But when you deallocate, you have to assume whatever you deallocating will no longer be there the moment you change the stack pointer. So you have to make that assumption. Yep.
You put that in the notes.
Oh, okay.
Yeah.
That's really good.
Yeah, that was nice.
Okay, so I would put it into subroutines, okay, and I'll put it here, okay. Memory content below where D points to can be changed asynchronously between any two instructions.
You said you typed between instead of below. You said below, but you said between.
Oh, okay. Below. There you go. That's because my thinking is already down to here.
Yeah, that's exactly what I thought. Because I do the same thing.
And I'm my typing is lagging behind, and then my buffer got overflowed, so overwritten.
Do you think we'll ever be able to, the inner monologue, when you think in your head, do you think we'll ever be able to harness that and be able to like go inner monologue to a file?
That would be interesting.
Yeah.
That would be very interesting.
Very confusing file.
I wonder how much thinking process can actually be represented symbolically. Okay, so when we are thinking, it is, most of the thinking is not symbolic. Unless you're talking, the monologue process is symbolic, and that's the whole point of talking to yourself or the rubber ducky, is you are forcing yourself to serialize the type of things that's going through your mind, and then integrating it back into the structure. So you're basically forming a loop, but it's a loop that involves a lot of symbolic processing, and hopefully that will solve the problem. But when you're not talking to yourself and you're just thinking about something, that process is most likely not symbolic, which means you cannot really just have a transcriber to transcribe exactly your thinking process, because you may be exploring multiple paths at exactly the same time subconsciously. So it's not a sequential kind of thing. It's not a serial process. So I think that it will be very interesting to see how that can actually be represented. If we have the mechanism to log it, right?
You have to create new ASCII characters.
Yes. Well, how would you log a taste, for example, or a smell?
Sensation of some kind.
Exactly.
Right? Yeah.
More ASCII characters.
Need new format.
More ASCII characters.
Or Unicode.
Well, I mean,
Yes.
obviously they can be represented, because it's just like with color, right? RGB. Okay, you have the RGB representation of most colors. But the RGB representation actually does not cover the entire gamut of what your eye can perceive, but most of it. A lot of the green colors cannot be displayed on monitors because they cannot be represented using just RGB, which is kind of interesting. You would think that everything can be represented, but it's not.
We can see more green
We're
colors.
least sensitive to green or something.
Huh?
As humans.
Because we're predators. What did you ask that? Or what did you say?
Yeah.
Because are we like the least sensitive to green color?
We're super sensitive.
Super sensitive, right?
Because we're predators.
Right. That's also why
No,
they
no.
make
You
colors
can
green.
have
It's not
super high resolution, like you can allocate
It's not
32
because
bits
it's
per
not
color,
like that.
and there will still be colors that is outside of the gamut of what a monitor can display, as opposed to what you can actually see in nature.
Well, sure, but
We evolved from
again,
green.
we're getting 10-bit
that's
color
true.
reduction on certain monitors, and I'm sure we're going to work our way up as we get better with the technology.
Maybe.
I'm sure on the computer we can represent a lot of colors, but yeah, the reproduction of colors can be
Am I
difficult.
like a tangent machine?
Okay. So getting back to this one, decompiling a program, you can certainly recognize chunks of code. Okay, so chunks of code that you should recognize. The first kind of chunk of code, I would start with these because it's the easiest. Is the return mechanism, which you usually find at the very end of a subroutine definition. Where you copy what the stack pointer points to a register, increment the stack pointer, and then jump using that particular register. So the return sequence is a very easy chunk of code to recognize because it's almost identical every single time. The call sequence is also easily recognized, where so in the call sequence, you load a particular register with a return address, you push it on the stack, right? And then you do an unconditional branch to the subroutine, and then the label corresponding to what you pushed earlier on the stack is right after that. That is the sequence of a call, and that is usually quite easy to recognize as well. Okay. What else? Chunks of code. How do you recognize a conditional statement?
The branches and jumps.
Conditional branches, okay? So when you look at conditional branches, then you have several possibilities, okay? Well, those, but also the structure, okay? Also the structure. So if you have a unconditional branch to an earlier label, that is almost certainly because of a loop. And the only loop that we use in this class are while loops. I have not used a do while loop ever in this class. So when you have an unconditional branch to an earlier label, that unconditional branch itself is marking the end of the while loop itself, the body of the loop. And then whatever label it branches to, the earlier label, is marking the beginning of the entire loop, which is the part where the condition of the loop is evaluated. So this is the kind of stuff or clue that you look for when you're decompiling a program. Okay. What if you have an unconditional branch to a later label?
It's an if.
That's most likely going to be an if going to a future branch or going to one of the branches, going around a particular branch also. So a unconditional branch to a later label usually indicates that you're dealing with a conditional statement. but that branch itself can be at the end of the then branch, you're branching around the else branch. But a conditional branch to a later label is going to be the branch to the else label. But it all depends on the polarity, because the conditional branches that we have can only branch when the carrier flag is set. What if you want to branch when the carrier flag is clear? Then you have to use an unconditional branch to get around that problem. Okay. What else? Okay. Updating register A right before return. Okay? Especially when the return itself is using something other than register A, but you update register A right before the return. What is that signifying?
You're returning a variable.
You're returning a particular value. Yep, exactly. So that means the subroutine has a return value, which also means you have to now go back and say, okay, what is the type of that return value? Yeah, all right. Dereferencing, okay? Dereferencing, okay? How do you know you are dereferencing something? I mean, the instruction set that we have is so limited that whenever you see a particular kind of instruction,
If you LDI, the exact same thing, but one's
not
present.
LDI, LD. LD and ST, okay? Either one, because it depends on whether you're storing something to where you're dereferencing to, or whether you're just reading from where you're dereferencing from, okay? But whenever you're dereferencing, you have to ask the question, what are we dereferencing? Because in the assembly code that we are dealing with, you're only dereferencing a register. So now the question is, what is in that register at the time that it is dereferenced? Are we dereferencing something that is pointing to a parameter, or are we dereferencing a parameter itself?
Would you ever give us something more extreme, like a pointer to a pointer?
That's possible.
It's possible.
So you have to track,
So
you know, how many times we are
yeah.
dereferencing. So that means it is really helpful when we have a question like this to decompile something. It is really helpful to track what each register has at a particular time in the algorithm. So you can say, you know, C is the address of the return address. C is the address of the first parameter. But if I dereference C back into C, now C is the value of the parameter, right? If I dereference one more time, then I'm dereferencing. So I'm using the parameter itself as a pointer,
Yeah.
and I'm dereferencing the parameter itself, which implicitly is telling me that the parameter is not an integer; it is a pointer to something. So that is giving you clues of, you know, what is the type of variables and parameters. Okay. Any other questions?
Did you go over data types?
Data types?
How to know what the data type is, if it's an int, float.
Well, we are not dealing with floats.
Oh, okay.
So we have ints, we have unsigned, we have, you know, basically they're chars too. Okay. But we also have pointers. We also have
So
pointers to
just
ints, pointers to
unsigned,
chars. Yep.
or char.
And potentially pointers to pointers. I mean, if you can deal with one level of pointing, you can deal with two levels or however number of pointers. Yeah.
So that count. So make sure ints, unsigned ints, chars, and pointers. That's it.
And I think the most, you know, one of the more kind of difficult questions would be nested calls. So in a nested call, you are utilizing the return value of a call, and you're pushing that on the stack to set up as a parameter for the outer call. So you have to kind of analyze those things, you know, first by recognizing that they are calls using, you know, recognizing the chunk of your call here. Then you have to look at, you know, how the return value is utilized. Is the return value, which is always in A, register A, is it just copied to another location, or is it pushed on the stack right away? If the return value is pushed on the stack right away, there's a pretty good indication that we're dealing with a nested call in that case. Is that okay? All right. So basically for everything that we can translate in compiling, you kind of think about, okay, when I'm looking at the code that is the result of the compilation, can I recognize the original C code from the assembly code? That is the question. So the more you exercise, the more you go through examples, then the better you can recognize those patterns. Is that okay so far? Okay. All right, so we have covered subroutines, C programming, decompiling, which is the reverse process. So there might be a question where I will give you the assembly code, and you don't have to decompile, but I'll ask the question of what is the result of running this code, which is one of the questions in exam 2. So with those, you don't really have a choice. Well, okay, you do have a choice. You can try to decompile first and look at the C code and figure out what the C code is doing, or you can just follow the code and just run it through. So you basically, you become the organic, logic sim, and then run that code through and figure out what is happening on the stack, with whatever the register is pointing to.
You haven't graded that one for question.
Not yet.
Exam 2. But we can look at the answer. Yeah.
Yep, you can look at the answer.
And ALU stood for what again? Is arithmetic and logic.
Arithmetic and logic unit.
Logic unit.
Yep.
So, actually, that reminds me of a question I had. So, you mentioned in a previous class that modern processors actually have multiple ALUs. Do they essentially utilize multiple ALUs by sending the first instruction to one ALU, and then then the next slice of code will send the next instruction to the, or next thing to the next ALU?
Yep.
So it cycles through the ALUs?
Yep.
Okay.
So it will schedule, what they call scheduling, is it will schedule these ALUs to correspond to this incoming stream of opcodes. Because even with the modern processors, many of the operations cannot be done within a single clock.
Yes.
So that means if it has to wait, really sequentially, then it will take a longer time. But if you can figure out that there are several instructions, they are doing different computations that are not interdependent, then you can schedule and go like, okay, ALU1, you do this operation, ALU2, you perform this operation, ALU3, you do that operation. So now you're operating all of those things at the same time, which means you're parallelizing operations as much as you can, so the overall throughput of the processor will be improved. But that is a hardware thing. In other words, when you write your code, you normally would not think about scheduling of the ALUs. You just kind of write the code the way you normally do,
right.
And then the processor is the one that has to go look at the incoming stream of instructions and do all that scheduling.
Right.
Okay, but if your compiler is cooperating with the architecture, then the compiler can actually try to order the opcodes to reduce the interdependencies between the opcodes as much as possible, so that the processor can now say, okay, we can now utilize 4 out of 5 ALUs in the same core and maximize the efficiency of computation. So that means it's not really just an issue with the processor architecture itself. It also relates to the compiler or the compiling of the code to try to like scatter things, to remove interdependency of sequential instructions.
Okay, thank you.
Which is actually a really kind of important thing, because it's not a trivial problem. Because there are many ways to order instructions. Which one will give you the maximized throughput, and utilize as many ALUs as possible is an optimization problem. And most optimization problems are what we call NP complete, which means they're kind of difficult problems to solve. So that's why when you turn on optimization with GCC, you will notice that with a longer source code, it will take a significant longer amount of time to compile. Has anyone tried that? With a relatively large program, to compare the speed of compiling between turning on versus not turning on optimization? No one. It actually makes a huge difference. I think it's almost like 4-to-1 or even more. It would take 4 times as much, 400% of the time when you turn on optimization to compile the same code compared to not using optimization at all. It can be even more.
This optimization, it benefits runtime, right?
It benefits runtime, and the runtime benefit can also range easily from with a 200% ratio. In other words, the code after optimization can run like twice as fast usually, but sometimes it can be even more. It depends on what kind of things is getting optimized.
You talked about that in the last class period, right? Like if you had a loop that only did like loop 2 times, well, there's no reason to make it a loop. Just write what it's doing 2 times.
Yep. So in that case, it depends on what you're doing, the body of the loop, whether that is taking a really significant of a time. If that portion is taking a significant length of time, then it doesn't really help to optimize the looping mechanism itself because it's only a very small percentage of the overall time. On the other hand, if it's a very quote-unquote tight loop, where the body of the loop only has one little thing to do that it can be done really fast, then unfolding the loop can really help in terms of efficiency, because it is possible that the checking, the incrementing, and the branching back is 400% of the actual time of what you really want to do per iteration. So in that case, optimizing the loop and unfolding it into just sequential instructions will help tremendously. So all of those topics, even though they're not exactly in assembly language programming, they're related to assembly language programming. And in the foreseeable future, they will still be in computer science. Yep. So any other questions about the decompiling techniques? I'm only outlining what's going through my mind at this point, because when I decompile code, I'm just relying on mostly intuition for the most part, so it's not exactly, it's intuition, followed by logical evaluation, but for the most part it's intuition, which is just like, okay, that's where I can go with this, how it relates to other pieces of code within the same subroutine and stuff like that.
This is going to be in the shared folder, right?
It is not yet. Okay, so if you want this to be in the shared folder,
Sharing is caring.
Sharing is caring.
Like me again?
Well, I'd like to be raising the curve of the class, which means to be less likely for questions.
okay, where should I put it?
What do you want to call this?
Tips.
Tips for finals.
Tips.
Just tips. Don't forget to tip your waitress.
As a folder.
Waiters. What about waiters?
Hmm?
I guess it could be a whole lot of different tips.
Well, I can add some more later.
You just put one word instead.
Okay, I'm going to rename it to. So now this pertains to the final exam, tips for the final exam. Okay. It doesn't suggest anything about the questions themselves, because even I do not know what questions I'll be asking. But it does pertain to techniques that you can employ or what you need to study, as far as the final exam is concerned.
Unrelated. The link. Do you know how they come up with the?
It's probably some kind of a hash.
Yeah. Because there's stuff like GiffyCat, which does just like a group of 3 words, which I think is really.
Yeah, so it's some kind of a hash. So these days it's probably a SHA-2 hash, because the other hashes are known to be not secure, which means that they can be reversed, and this one is probably a much more secure hash. So it's probably a hash from some kind of sequential number that starts. May not even be a single hash. It can be a hash based on my username and a few other things. Because you don't want to be able to reverse that. If you can reverse that, then you can kind of you can try to hack. In other words, you can just try to go like, okay, I know this is text folder. This doesn't tell you anything about my folder structure whatsoever, which is intentional. Because it is actually easier from Google's perspective to make this path also follow the path from my share folder, but that would disclose structure of my folder structure, which means hackers can now say, okay, tech only gave me access to a particular document, but if I can reverse back to the path, then I can see, okay, can I get to the folder itself? Then can I see other files and so on and so forth? Using this, you cannot reverse engineer.
Unlike a file path, you can't actually see where it came from. You just see
Exactly.
what it is.
You don't even know who owns it.
Yeah,
Yep.
it's pretty cool.
Yep.
So could you technically, theoretically, replace one of those
Characters and
go to some random person's documents, assuming
Yeah,
that
absolutely.
matches?
So you can,
Good luck with that.
You can change these things, but the question is is that matching the hash value of an actual folder or document?
Right,
Oh,
it's
So
wrong.
yeah, exactly. We are talking about how many characters here.
40 characters.
It does on YouTube.
Hmm?
You mess with it, it's not.
Okay,
That's a lot,
so
yeah.
The difference is whether or not you're allowed
It's a
to.
random
Google will
user.
still check like,
Yeah.
okay, what the
Secure,
hell are you
yeah.
doing over here?
Yeah.
Right,
They-
but-
they
but-
probably have some sort of.
but there is the issue of I can share a single folder, but I do not give anyone a link to the folder itself, and then I give links to individual documents within the folder, because I don't want people to know what else is in the folder. So if you can reverse engineer back to the folder itself, then you can see all the documents in that folder, which is not something I want to publish.
Yeah, it should be like a comment.
So what I'm doing here is I'm just pasting it here to count the number of characters. So it looks like, okay, I'm just gonna do a quick thing here.
Just go in the word into word count.
Okay, it looks like 45 characters or so.
That works.
So it looks like 45-ish. And this is what they call, I think the last three may not be a part of the scheme. This is what they call Base64 encoding, which means each character is representing 6 bits.
6.
6.
Why 6?
Because they are using all the digits, they're using all the lowercase and all the uppercase.
Yeah.
So together, each character is one chosen from 64 possibilities, and 64 possibility means you can represent 6 individual bits. So now we're basically looking at 240 something bits, which sounds like a SHA-2 type of hash function. Which also means if you change one of these characters, the chances of that hash matching another document that is in the same share folder when you have access to it is pretty slim.
It's more better using your time to study than try to find the answer.
Ooh, Base64 conversion. That might make a very good final question.
Well, you said
Spaces on that script.
Wait, it's a code. Base64 what?
Base64 encoding and decoding.
Okay. That's just saying.
Yeah, I'm just saying.
No, I don't
Say it
want
out
to see my
loud.
final. I want good questions on final and answer.